Have you ever just stopped and really looked at a leaf? I mean, it's basically a tiny, perfect factory. Every single day, it's quietly performing what is honestly a miracle. It turns sunlight, the carbon dioxide from the air, and a little bit of water into pure energy. It's pretty much the most elegant chemistry on the entire planet. So that brings up a massive question for scientists and engineers. How in the world does nature do this so flawlessly? And if we're trying to create our own clean fuel, why is copying a simple leaf one of the hardest challenges in all of science? Okay, let's get into it. So to really get the challenge here, we first have to appreciate just how genius the original is. Natural photosynthesis is this incredibly sophisticated, fine-tuned process that's been perfected over billions of years. It's the absolute gold standard that scientists are, well, desperately trying to replicate in a lab. The dream is actually pretty simple to say out loud, but it's incredibly difficult to pull off. Build an artificial leaf. A device that could take carbon dioxide, our biggest climate headache, and water, and then use sunlight to turn them into clean, storable fuel. It would be a complete game changer for energy. But for decades, this dream has just kept hitting a wall, a really fundamental roadblock that has stopped so many attempts dead in their tracks. And it all comes down to a problem of timing. See, artificial photosynthesis has two main jobs that are in total conflict with each other. First, you have to split water. This is a fast, almost explosive chemical reaction that, boom, instantly frees up a burst of electrons. But the second job, converting CO2, is the total opposite. It's this slow, complex, multi-step process that needs those electrons delivered in a slow, steady stream. And this visual illustrates it perfectly. Just imagine two gears trying to work together. The water-splitting gear spins like crazy, while the CO2 conversion gear turns slowly and carefully. So what happens when you try to connect them directly? Well, they jam up. The whole system breaks down, energy gets wasted, and everything grinds to a halt. This is the timing problem. So how do you solve it? For years, scientists were trying to invent some kind of new gear, a new solution. But it turns out the answer wasn't a new invention at all. Nope. The answer was hiding in plain sight, in a secret that nature perfected about 1 billion years ago. A real leaf doesn't connect to its fast and slow processes directly. Instead, it uses a molecular middleman, this brilliant little go-between called plastoquinone, or PQ for short. And it is the absolute key to the whole operation. Okay, so this is the crucial point. Plastoquinone acts like a tiny, rechargeable battery, or maybe a buffer. It soaks up that initial, chaotic burst of electrons from splitting the water, holds onto them, and then it feeds them out at the exact steady pace that the CO2 conversion process needs. It decouples the two reactions. It solves the timing problem. And this is where the breakthrough happens. A team of researchers decided, hey, let's stop trying to reinvent the wheel. Instead, they decided to learn directly from nature's playbook. They set out to build their very own version of plastoquinone, a material that could act as that perfect middleman. And here you have it, straight from the source paper. The inspiration was totally explicit. They designed a new material, this silver-modified tungsten trioxide, specifically to function as what they call a charge reservoir, a direct mimic of nature's strategy. This slide just shows the parallel perfectly, right? On the left, you've got nature's system with its plastoquinone buffer. And on the right, you have the new artificial system with their silver-modified tungsten trioxide playing the exact same role. It's bio-inspiration in action. So what exactly is this charge reservoir? Well, it's a material that's designed to do one thing really, really well. Trap those fast, short-lived electrons from the water-splitting reaction and then convert them into a stable, long-lasting supply that can be drawn on whenever it's needed. So here's how it works on an atomic level. When sunlight hits the material, it uses that energy to store an electron by changing the charge state of a tungsten atom. You can think of it like flipping a switch from off to on. And that on state is stable, holding the electrons safely until the CO2 conversion side of the reaction asks for it. So the big question is, does this bio-inspired strategy actually work? Well, the results aren't just an improvement. They are a staggering, unbelievable leap forward. 100 times. No. That's not a typo. By adding their charge reservoir to the system, the researchers enhance the production of carbon monoxide, a key building block for fuel, by a factor of 100. That's compared to just using the main catalyst all by itself. This chart really puts that number into perspective. I mean, look at the tiny little output from the catalyst working by itself. That's basically where the field was stuck. Now look at the massive bar next to it, the output when it's paired with the charge reservoir. It's a night and day difference, and it's all thanks to solving that fundamental timing problem. And here's why this is so important. This level of efficiency, before, was only possible by kind of cheating, by using these so-called sacrificial organic chemicals that just get consumed in the process. It's not sustainable. But this new system, it achieves that same high performance using only water, just like a real leaf. Now, this breakthrough isn't just about one specific material. It's about proving that a universal strategy, one we copied from nature, can unlock the future of solar fuels. And the researchers proved it. They showed that their charge reservoir isn't just a one-trick pony. It also dramatically boosted the performance of other common catalysts, like graphitic carbon nitride, which is a metal-free catalyst, and cuprous oxide, a simpler copper-based material. This suggests the middleman approach could be a universal key for a whole bunch of different artificial leaf designs. So the main takeaway here is this. By borrowing a billion-year-old idea from a leaf, we can finally decouple the fast and slow halves of artificial photosynthesis. We can finally solve the timing problem that has held this entire field back for decades. And that leaves us with a truly exciting thought. I mean, for so long, we've just seen CO2 as a waste product, right? A problem to be buried. But what if this is a beginning of a whole new way of thinking? What if by learning from a simple leaf, we could finally turn our biggest liability into our greatest asset, an endless source of clean fuel, made from nothing more than air, water, and sunlight?